So it's great to see that so many people are still here. I thought I was going to be alone with my supervisors. So I'm going to talk about the filter bank approach to earthquake early warning that I've been working on with Tom Heaton and John Clinton. Quick overview. I'm first going to motivate it. Basically, we want to minimize the blind zone and speed up earthquake early warning by thoroughly exploiting available waveform information. We do this with the filter bank, which is an optimal tool to evaluate the time-dependent frequency content in real time. And then I would like to present our algorithm, how we do parameter inference, in which we jointly estimate source station distance and event magnitudes based on single earthquake records. And then I'm going to show the results and make some concluding remarks. So to expand a little on the motivation, as you all know, earthquake early warning is a race against time. And in particular, we have the blind zone issue, which means that there is an area where we cannot provide warnings where they would be most needed. This problem is particularly acute for medium-sized events like the 1933 Long Beach event, or also the Napa Valley earthquake that we've talked about already a couple of times in the last 2 days. Because these events can produce severe damage, but the damage is limited both in space and time to relatively small extents. And so it's really tricky to be fast enough with any earthquake early warning algorithm to provide warnings that are useful. And so proximal sites to the epicenter will at best get only the earliest of warnings. Even if we're fast enough, they will only get the earliest warnings, and that's all they get. And so these warnings will always be based on very little data. And in this project, we're trying to optimize these early warnings, or the earliest early warnings, to optimize them when little or nothing is known about the source. And here, I think the waveform frequency content is the most readily available and diagnostic information source that we can have. And frequency content is mainly determined by magnitude and source station distance. So on a qualitative level, if we see high amplitudes at high frequencies, we know that we are looking at the near field observation. If we have high amplitudes at low frequencies, it tells us that we're looking at a large magnitude event. And if we observe both, we know that this is probably a case for earthquake early warning, and then we should send out a message. And so basically, within this frequency content is all we need for earthquake early warning, information on magnitude and the source station distance. So but how do we measure the frequency content in real time? And we do this with a filter bank. And the filter bank is basically, or the filter bank that we use is nothing but a set of causal bandpass filters. We use fourth order Butterworth filters, 9 of them between 0.1 until 48 hertz. They're all octave wide. And so these are minimum phase filters. So here you see the impulse response for different frequency bands, and you see that the longer periods, they're delayed more than others, but because it's minimum phase, it's the minimum delay that is possible in a causal system. And what's important, of course, for early warning, it's they're computationally cheap and they're perfectly applicable in real time. So what we run this filter bank on is an extensive and what I call a maximally objective near-field record data set. We have data from Southern California. We have Japanese strong motion data and a portion of the NJ West 1 data set. In total, it's 130,000 traces from 5,090 events. Actually, last night I added the Napa Valley earthquake, so now it's 5,091. And then we pass each trace of this data set through the filter bank so that we get for each trace 9 filtered traces. And on each we measure peak ground velocity as a function of time since the P wave onset. And then we term this quantity that we measure, or these peak amplitudes, narrowband peak ground velocity. And so now in the parameter inference, we want to use these narrowband peak ground velocities to estimate the source, or the parameters we're interested in for early warning, the magnitude, and the source station distance. And I'm going to present the algorithm first, theoretically describe what I'm doing, and then show it at this example of a near-field record of the Napa Valley event. I noted there that it's 4 kilometer high percentile distance. That's probably wrong. It's some error in my computation or in the header information of the waveform. But it's not terribly important, I think. So there's 5 steps to the algorithm. So first we have or no, I got to say the starting point is the target trace, so the trace that we would be looking at in real time. And we have a training data set that consists of all the other traces that we have in the data set. And for these, we have pre-computed these narrowband peak ground velocity values, and we use them all as training data, except the other traces from the same event. So we take this target trace and we measure the narrowband peak ground velocities in the different frequency bands with all the data that we currently have. So say we have 2 seconds, so we measure the peaks in there. And then we compute the similarity of this target trace to all the other traces in the data set using this similarity criterion, where the similarity is just a sum of the difference, a sum over all the 9 frequency bands, summing up the squared difference between the target trace and the training data amplitude. And then we're going to extract from this training data set N or NSIM most similar earthquakes or traces. And we take the magnitude values and the distance values of these most similar traces. Once we have done this, we can approximate these parameter values with a bivariate Gaussian to get an empirical likelihood function of the magnitude and the source station distance given the observed peak amplitudes that we made on the target trace. And eventually, we can treat either of the 2 parameters of this likelihood function as a nuisance parameter and single out the univariate profile likelihood functions and then maximize those to find the best parameter estimates. Now that sounds probably a bit more complicated than it actually is. Here's the example of the Napa Valley earthquake. So on the top left, there's the 3 examples from 3 pass bands that I've singled out. Yellow line is the P-peak, and then the red cross marks the peak velocities that we've so far observed, and the purple line is the end of the time window that we're looking at. So this corresponds to ½ a second since the P-wave onset. In the bottom left plot, these are the peak amplitudes that we observed in the 9 frequency bands. Again, the red crosses is the target trace, and the colored line in the background, that's the 30 most similar traces that we have in the training data set. And then we take the magnitude and the distances of those most similar events, and we plot them as yellow circles in the top right. So that's the data that we use to quantify or to parameterize the bivariate likelihood function. And the bivariate likelihood function you see on the bottom right as a color map is actually the relative log likelihood function. And then having this empirical likelihood function for the 2 parameters, magnitude and distance, we can single out the profile likelihood. So for example, if we're interested in magnitude, this is the profile likelihood function of the magnitude. And it's just at every magnitude level, we maximize this likelihood function with respect to the distance and take the corresponding likelihood as the likelihood value for the profile likelihood. And the maximum of this is then our best parameter estimate. And the nice thing about this formulation is that then once you have this univariate profile likelihood function, for example, for magnitude, you can very easily combine estimates from different stations once, for example, a second station is triggered. And now, so this is after ½ a second. Now if we move on to a full second, you see that the peak amplitudes changed. And by the way, on the top right corner, you can see the magnitude estimate. The white lines are the true values. So you can see that already after 1 second, we're getting magnitude 6. So that's working kind of nice. And then as we move on through the waveform, we get different amplitudes, different training data, traces, different magnitude values. Hopefully the distribution will become more narrow, so we're more certain about our parameter estimate. So that's basically the algorithm. And so this probabilistic formulation, as I've already mentioned, has important advantages. So we can easily combine magnitude estimates from different stations. Or what's also important, that if additional constraints on either one of the 2 parameters comes in, for example, if we have a distance constraint from S-phase peak, we can just feed this back into the likelihood function, combine it, and update our parameter inference. So once you have the probabilistic formulation, everything's pretty straightforward. And so here's the result for all the 5,000 events. The top one shows just for one single station the magnitude prediction. So y-axis is magnitude, predicted magnitude minus the true magnitude or the catalog magnitude. So positive values is an over prediction, and x-axis is the true magnitude. So and just 1 second at the first triggered station is used. And you can see that already there's some predictive values for this parameter estimation. But you also see that we have a very distinct magnitude saturation that we need to further work on, and hopefully we think we have ideas how we can make this better, but it's still a work in progress. On the bottom you see the results once the third station has 1 second worth of data, and then you're already at plus minus 0.3 magnitude units error, but you still have the saturation issue. Oh yeah, I forgot to say, here we actually assume that we do have an additional location constraint, that we know the location to within plus minus 10 kilometers. So for the single station on the top, that's not very realistic, but for the bottom, it's probably not too bad an assumption. If we don't make this assumption, we get this, so we get somewhat more scatter and a little bit of bias for the small magnitudes, but it doesn't change the picture too much, I would say. So to wrap up, this is a novel approach for inferring magnitude and hypersample distances in real time based on single station records. We have little bias and very little scatter for very small amounts of data, so that is really good, so that we can use it as a basis for warning messages in the blind zone, but we have the problem of the magnitude saturation. The probabilistic formulation makes that it's straightforward to update parameter estimates as new data comes in, to combine the estimates from different stations, or to add independent additional constraints. And as a side mark, the method includes the interdependence between the uncertainties from the distance and the uncertainty from the magnitude in a systematic way. So we're currently working on how we can avoid the magnitude saturation. For example, we could use adaptive weights in the similarity criterion. For example, to upweight low frequency observations when overall amplitudes are high. Or we could actually go to a skip or abandon the non-parametric approach and go to a parametrized approach. And because the algorithm is at least partly based on different data than ELARMS, on-site, Presto, and so on, there could be an information gain when we can use the algorithms together. That's it. Thanks.
Thank you. Questions? John.
So if you're putting all the records from all over the place together, I mean, you may be building in kind of attenuation structure, velocity structure, other than you know is near the station. So you're hoping that'll all average out, or, I mean, would it make sense to throw out the wrong geologic regions and the records recorded there?
Well, we looked into this and we didn't see two important differences between the different regions, and the overall scatter that we have anyways, I think, is larger than those systematic differences between the regions. And also there's been the study by Kuyuk and colleagues where the result was also that the best results you get if you take all the data, even if you do mingle different regions.
So East Coast versus West Coast, the attenuation differences don't matter that close in?
Well, maybe East Coast versus West, well, there's no East Coast data in here, but Japan and California, apparently you can mingle. All right.
So the idea here is to use this for a single station approach. And so there was a trade-off between the distance and the magnitude. I mean, you showed that as in the example you gave. It went by too quickly for me. How bad is that trade-off? I mean, what's the range of the uncertainty in the magnitude and the range of the uncertainty in the distance?
I would say that's it's a bit different for each record. There's sometimes they're very well constrained in distance, sometimes they're very well constrained in magnitude. Sometimes neither of both. But the idea behind the algorithm is that by combining the different frequency bands, you can actually resolve this trade-off to a certain extent. Because if you're looking at any single frequency band, an amplitude of a certain height can always be from a small magnitude nearby or a bigger one further away. But this, if you look at different frequency, you no longer have this trade-off to...
I guess I'm asking because it looked like the specific example you showed, which is just one obviously had a bit of a trade-off.
Yeah, can maybe go back there.
Yeah, right. So this here, the trade-off between magnitude of 4 to 6 versus a distance of...
Yes, they always line up in this, you still have this trade-off, but by maximizing then the likelihood function, you get the most likely value, and it typically corresponds to the true value. You do have the problem, that's why it helps adding the hypercentral constraint. So for example, in the results, where is it? You see that the downward slope for the small magnitudes, if we don't have the distance constraint, is much more pronounced than if we do have the distance constraint. Does that make sense?
Yeah, I believe the site application factor is also an important factor to determine frequency contents of the waveform. Site application factor. So if you correct the site application, I believe more reliable estimate can be possible.
Yeah, we thought about that. The problem is that the site amplification factor would be both magnitude and frequency dependent. So in different frequency band, you would have to correct it. It'll be pretty complicated, I guess. I'm not sure if you'll end up with something better in the end. You add a lot of complexity also.
But not only the source factor and frequency factor, also site factor is also the frequency dependent. So it's a site frequency is the removing site corrections. So I believe more reliable estimation is possible.
Mm-hmm. Well, the way I understand it is that this is very important for, say, magnitude 2 to 5, but once you go above a certain amplitude level in your record, then it's no longer so clear what site correction you should apply. But we should certainly try it. I agree with that.
In looking at this plot, it would seem that the underprediction around magnitude 6 has a slope of about -1, which would mean that the earthquakes look very similar. I was wondering if you could comment from what your insight is about the beginnings of the big earthquakes, how similar or different are they as a function of magnitude?
Yes, well, I think that, to me, it's still not clear I think we can still improve the algorithm so we don't get this full saturation that we currently observe. But part of it could also be real saturation that is also visible with other algorithms. In fact, I wanted to try the tau p max based algorithm, which tend to saturate less from past literature, because I think this is a larger data set. But it's not. I think it's not fully established at what point we would have to expect a saturation. But I would like to look into this in the future. But here, I think it's a significant fraction of this is due to the algorithm. And the reason is because of the non-parametric approach, that when you're looking for the most similar traces in your data set, if you're at the upper end of your data set, all the most similar ones, they will be lower. And so because we have still very little near-field records of, say, magnitude 7 and above, that this draws down your magnitude estimate.
Yeah, if you're only using 2 seconds, 1 second or 2 seconds data, it's hard to represent a 10-second time series, the spectrum of a 10-second time series with 1 second of data.
Yes, but the fact that it works actually tells us that magnitude 6 events at the first seconds already look different than, say, magnitude 5 event.
But not than a magnitude 7.
Yes, but we don't know how much of this is... Well, actually, that's another figure that I would like to show. As I said, this is probably because of the a drawback of the algorithm, because the amplitudes, they are different even for 7s. So here, in this curve, the red ones are magnitude 3s, the cyan ones are magnitude 5s, and the yellow ones are magnitude 7s. That's two median values for all these same kind of spectrum curves. Median values at 3 seconds this time after the P wave. And then there's 3 solar station distances for each magnitude. And you see that the magnitude 7s are distinctly higher than the magnitude 5s.
But how many seconds do you have in these spectra? These are 10 seconds worth of spectra? Or 1
3
second
seconds. This time it's 3 seconds. It's
They're not spectra that filter banks.
yeah,
It's the
not-
same.
It's probably a bit wrong too. It's more like a wavelet transform that you get. It's a time frequency representation.
Sounds like a great discussion to have over beer.